Ever look up at a massive stadium roof or maybe drive across a sprawling steel bridge and just wonder, how on earth is this thing actually staying up? Well, today we're going to look right through all that concrete and steel to uncover the hidden structural heroes holding up our modern world. We're talking about the ultimate architectural workhorses, trusses. Welcome to The Explainer.
Here's a quick roadmap of where we're headed today. 1. The mystery of giant structures. 2. What exactly is a truss? 3. The magical equation of stability. And 4. How engineers analyze them.
All right, let's jump right into part 1, the mystery of giant structures.
Seriously, think about this for a second. How do massive roofs and bridges support immense weight without snapping under their own load? Gravity is a relentless, totally unforgiving force. When you try to span a really wide distance, like over a rushing river or a huge sports arena, the sheer weight of the building materials alone is often enough to trigger a complete collapse. And that's before you even add the dynamic weight of cars, trains, or a heavy winter snowfall. Historically, builders using solid stone hit a wall. They could only build so wide before their magnificent arches and domes just gave way and collapsed under their own massive bulk. And the answer to going bigger isn't just use thicker steel or stack more stone. That literally just adds more dead weight, compounding the problem. The real answer, it lies in invisible forces and some incredibly clever geometry.
Which perfectly tees up part 2, what is a truss?
So to solve this heavyweight problem, humanity had to get really smart. A truss, or as it's perfectly known in Arabic engineering context, al-jamalanat, is an incredibly elegant solution. By definition, it's an engineering structure consisting of long, straight members with small cross-sectional areas used to carry loads over a wide span. Basically, think of it like a skeleton. Instead of relying on one massive, heavy block of solid material, engineers use a carefully calculated network of slender, lightweight bones. These bones are arranged perfectly to share all the heavy lifting across the entire span. It is honestly the ultimate exercise in maximizing strength while completely minimizing the material used.
But how do these straight beams actually come together to form this unbreakable skeleton? Well, there are some very strict, non-negotiable rules in truss design. First off, the members are connected only at their ends via joints, which we also call nodes. You'll see these connections made using hardware like pins, hinges, or rivets fastened to a gusset plate. Second, and this is absolutely crucial, loads are applied only at these joints, never, ever in the middle of a beam. Because of this, the internal forces act purely in tension or compression along the axis of the members. There's zero bending force. This setup naturally forms a network of triangles. And geometrically speaking, triangles are the only polygons that cannot be deformed without changing the length of their sides. So this locks the entire shape into a completely rigid, stable form.
Now, we can generally categorize these incredible frameworks into 2 main types. First up is the planar truss. This is where the structure and the applied loads all lie perfectly flat in the exact same 2-dimensional plane. If you've ever walked past a residential construction site and noticed standard wooden roof frames being hoisted up, yep, those are planar trusses. On the flip side, we have the space truss. This is your massive 3-dimensional geometry where the structure, the applied loads, or both exist in multiple different planes. Think of a sprawling electrical transmission tower stretching up into the sky, or the sweeping, intricate dome of a modern stadium.
Moving right along to part 3, the magical equation of stability.
Okay, now that we know what a truss, or al-jamalanat, actually looks like, how do we prove it's not going to fall down? To prove a structure is statically determinate, meaning we can mathematically guarantee it's perfectly stable and solvable, we use a foundational formula, represented here with Arabic engineering variables. Now, it looks like a relatively simple algebra problem, right? But it holds the absolute secret to structural integrity. The equation is 2 ta equals dod plus ra. Let's decode exactly what this notation means and why it literally dictates whether a bridge stands or falls. Think of this formula as our universal recipe for stability. The symbol ta stands for the joints or nodes, those crucial connection points we just talked about. Dod represents the members, the straight beams themselves that form the triangles. And finally, ra stands for the external reactions at the supports. Put simply, a reaction is the upward force the ground, a wall, or concrete pillars push back with to fight gravity and hold the whole thing up. For a standard balanced structure, this is usually a value of 3. So the rule is brilliantly strict. If you multiply the number of joints by 2, that number must perfectly equal the total number of members plus those external reactions. If this beautifully simple equation balances out, boom, your structure is stable.
And it's amazing because all these vastly different frameworks, from incredibly tight repetitive triangular patterns to wide sweeping arches that look almost delicate, ultimately obey the exact same mathematical recipe. The geometry can look vastly different depending on the specific architectural needs of the project, right? An engineer can get incredibly creative with the design. But no matter how unique the silhouette is, the underlying math is completely universal. Every single functional truss design strictly balances its joints, members, and external reactions to stay rigidly in place against the crushing force of gravity.
Which brings us to our final section, Part 4, How Engineers Analyze Trusses. So, we have our rigid geometry and our foundational formula for stability. But before crunching any heavy numbers to figure out the exact forces acting inside those beams, engineers have to simplify the messy, unpredictable physical world into a clean mathematical model. Because in reality, joints have a little bit of friction, and heavy steel beams will bend ever so slightly under their own weight. But by making 3 vital assumptions, engineers essentially turn an impossible physics nightmare into a solvable geometric web. First, they assume all members are connected by perfectly smooth pin joints, meaning absolutely no friction is twisting them. Second, they assume loads act solely at the joints and within the same plane. And third, they assume the longitudinal axes, the imaginary center lines running straight through the members, intersect perfectly at a single microscopic point right at the joint.
Once those simplifying assumptions are locked in, this is where the magic really happens. Engineers begin a step-by-step detective process. Step 1, they determine if the truss is actually stable and statically determine it using our magical formula. Step 2, they draw a free body diagram. This is a crucial mental leap where they completely isolate the structure from the ground and replace the physical supports with mathematical reaction force symbols. And finally, step 3, they calculate those exact external reaction values using the core equations of equilibrium. This ensures that the sum of all forces pushing horizontally and vertically perfectly equals 0. Literally, every single ounce of force must be matched and countered.
It's truly fascinating, isn't it? How our largest, most imposing modern infrastructure ultimately boils down to slender, lightweight members, perfectly rigid joints, and elegant mathematical equilibrium. So I want to leave you with this thought. Tomorrow, when you step outside and look up at the soaring highway bridges or the exposed warehouse roofs spanning vast spaces in your city, will you just see a random jumble of steel and wood? Or will you be able to spot the hidden geometry and invisible math working tirelessly to keep you safe? Keep an eye out for the hidden math holding up our world, and I'll catch you in the next explainer.